Okay. Okay, thank you. I would like to thank the organizers for the invitation. Today, I will talk about the global Calderon Zygmund theory for parabolic p-Laplacian system. This is based on a joint work with Ke from Fudan University and Hong from Chinese Academy of Sciences. First, I will talk about the introduction and the main result. We consider the following inhomogeneous parabolic p-Laplacian system, which read as system 1 here. And AXT is the coefficient of the system, and U equals 0 on the parabolic boundary of omega t. Omega t is a space-time domain, and it is omega times 0 to t, and omega is a bounded open domain with a C2 boundary, and the F here is in LP. The coefficient A is bounded above and below for any xt in omega t. We call that U is a weak solution of system 1 if U belongs to this space and satisfies the following equality for all test function phi. And the purpose of the Calderon Zygmund estimates is to explore whether the solution U is as good integral as the inhomogeneity F. That is, if we have F in LQ for any Q greater than or equal to P, can we get gradient U in LQ? Let us first mention some previous results in related directions. For the elliptic case, that is partial TU equals 0, Ivanik considered the scalar case, that is U is a scalar, and proved that the Calderon Zygmund estimates for any Q greater than or equal to P with P greater than 1. And after that, the Benedetto and Manfredi considered approved the same result for the vectorial case, that is U is a vector. And Quinones and Zhao extended the result to the elliptic equations with vanishing mean oscillation coefficients, and they proved the local Calderon Zygmund estimate. In 2005, Ashabi and Menjuni established a general Calderon Zygmund theory to the elliptic equations and systems with non-standard growth conditions. And for the global result, Quinones and Zhou considered the elliptic equations with VMO coefficients and on C1 alpha domain with Dirichlet boundary condition. The problem in parabolic case is more complicated. The main obstruction is the non-homogeneous scaling behavior with respect to space and time in nonlinear case. That is the case when P not equal to 2. And in this direction, the first result was proved by Misawa in 2005. They considered the case P greater than 2n over n plus 2 and assume that F is in L infinity. Especially in 2007, Asabi and Minjoni obtained a significant result. They considered the case P greater than 2n over n plus 2 and assumed that the coefficient A is in VMO and bounded below and above. They proved that if F is locally LQ, then gradient U is in locally LQ for any Q greater than or equal to P. The main idea of their proof is the intrinsic geometry for the upper level sets of absolute value of gradient U and the maximal function free approach. After that, Duza, Minjoni, and Stefan employed the idea to get the estimate for more general system like this. And Bjorn, Oak, Ruan, they also considered the case when p greater than 2n over n plus 2 and get a global result for a more general system like this in domain when omega is a Rothenberg flat domain. We can see from the above results that the range p greater than 2n over n plus 2 is always unavoidable. So why? It is mainly because of the structure of the homogeneous system. That is the system with f equals 0. Let us look at the classical parabolic p-Laplacian system. For this system, Di Benedetto and Friedman proved that gradient W is locally bounded when p greater than 2n over n plus 2. And from the paper of Di Benedetto and Herrero, and also the book written by Di Benedetto, a counterexample was given to show that omega can be not locally bounded when p is greater than 1 and less than or equal to 2n over n plus 2. The main reason is that W is a weak solution and it lies in this space, and this space is embedded in this space. It's LP times n plus 2 over n, and this number is less than or equal to 2 when p lies in this range. So we cannot get we cannot improve the integrability of W from iteration. After that, Cho proved that if W is in locally LR with R greater than n times 2 minus p over p, then a gradient W is locally bounded. When p is greater than this number, then this number is less than 2. W in L locally LR is implicit in the notion of weak solution, since in the definition of weak solution, W is in locally L2. When p is greater than 1, less than this number, n times 2 minus p over p is greater than 2, and this time W in locally LR becomes a restrictive condition. So there are no such Calderon Zygmund estimates for the inhomogeneous parabolic p-Laplacian system. And in this talk, we will consider the case p greater than 1 and less than 2n over n plus 2, and prove that for any q greater than n times 2 minus p over 2, if f is in LQ and the coefficient a has a small BMO norm, then we can get a gradient U in LQ. Here we mentioned that this number n times 2 minus p over 2 is greater than or equal to p when p is in when p satisfies this. And here a sub R0 is defined by 3, and in the following estimate, we will always do the estimates on in intrinsic cylinder. So use the idea of the Benedetto and also use the idea of Asafi and Mijoni. We also define the intrinsic cylinder here. It is Q lambda R. It equals BRX times minus lambda to the power P minus 2 R squared plus T to T. And here is our main result. Let Q greater than this number and omega be a bounded domain with C2 boundary. Let U be a weak solution of 1 with F in LQ. Then the LQ norm of gradient U can be bounded by LQ norm of F and plus LP norm of F to some power, provided that A has a small BMO norm. We give two remarks here. The first remark is our result is the first homogeneous result in the sense that U equals 0 if the data F equals 0. It is obviously from the estimate. And the second remark is that our theorem can be extended to Rothenberg flat domain. In the second part, I want to show how to the sketch of the proof. When proof theorem 1, we need a key theorem. This is theorem 2 here. It tells us that there exists an H such that for any eta kappa 0 between 0 and 1, and any sigma 1 between this number and n plus p, the L sigma 1 norm of gradient U minus H can be bounded by the right-hand side. We denote it as K. And here the point is we need the L sigma 1 plus kappa 0 norm of gradient U to bound the left-hand side. And sigma 1 plus kappa 0 is it is larger than sigma 1. However, we have a small factor here, eta. Eta can be sufficiently it can be small enough. And the second estimate shows that the L infinity norm of H can be bounded by the L sigma 1 norm of gradient U plus the above K. And by using theorem 2, we can prove the good lambda inequality. Let M lambda denote the Hardy-Littlewood lambda maximal function defined by 4. It is the average of the absolute value of F on the intrinsic cylinder Q tilde lambda rho. And then we can get the good lambda inequality. For any positive epsilon, we define U lambda epsilon as this set. This set is corresponding to the L sigma 1 plus kappa 0 norm of gradient U. And then there exists constant delta depending on epsilon, and also small, and lambda, a positive lambda, such that 6 holds for any positive lambda less than lambda 0. 6 tells us the measure of this set capital U lambda epsilon can be bounded by epsilon times the measure of this set. We remark here, we add U lambda epsilon here to deal with the L sigma 1 plus kappa 0 norm in the proof of theorem 1. And from the definition of U lambda epsilon, we see that there is a factor epsilon to the -1 here. To deal with this factor, we will use the small factor eta in comparison estimate. So this is one of the key ideas. And next, we show how to prove theorem 1 by using theorem 2 and good lambda inequality. For any q greater than this power, we can find the sigma 1 and the kappa 0 such that q is greater than sigma 1 plus kappa 0, and sigma 1 satisfies this. And from the definition of LQ norm of gradient u in omega t, we can get this equality, and we split this integral into two parts. One part is I1. In this part, alpha is small, and the second part is I2. And alpha here is large. And for I1, it is easy to estimate, and we skip the detail, and Olin point out that in the estimate there will be epsilon times LQ norm of gradient u in the estimate of I1, and then we focus on the estimate of I2. The key part is to estimate the measure when gradient u is large. Here alpha is here in I2, alpha is large. We let lambda equal 1 over alpha, then lambda is small. So we can use a good lambda inequality to get the set of the measure of this set can be bounded by this the three part here. And the red part is corresponding to the L sigma 1 plus kappa 0 norm of gradient u. And by the weak type 1-1 bound of maximum function, we can bound the measure of this set by the three integral. So how to deal with this the red part? We after integration with respect to alpha, we can get I2 can be bounded by this, and here we will use the Fubini theorem to change the order of the integral. Note that here gradient u is greater than alpha over 2 epsilon, so alpha will be less than 2 epsilon times gradient u, and we first calculate the integral with respect to alpha, and we can get epsilon times gradient u to the power q minus sigma 1 plus kappa 0, and then times this and this, we can get this part being bounded by epsilon to the power q times the integral of gradient u to the power q in omega t. And the other two parts of L sigma 1 norm of gradient u and F2 sigma 1 can also be bounded by the same way. Finally, we get the estimate of I2 can be bounded by a constant times s here. S is epsilon times this, and 1 over delta to the q times this. And combining the estimates of I1 and I2, we can get the LQ norm of gradient u can be bounded by the right-hand side. Let us take epsilon small enough to get to get this power, this factor less than 1/2, then we can determine the corresponding delta and the corresponding C epsilon. Therefore, we absorb this term by the left-hand side. We can get the result. So we finished the proof of theorem 1, and it remains to prove theorem 2. We prove it by 3 steps. The first step is the comparison estimates. We will compare the solution of the system 1 with the solution to the system 10. Here, system 10 is a homogeneous system with the coefficient being AT sub B to R. It is the average of A on in B to R, and W equal U on the parabolic boundary of Q lambda to R. And this is our comparison estimates. It is one of the key part of our proof. We get 2 comparison estimates. The first one is LP norm of gradient U minus gradient W can be bounded by the LP norm of F plus the L sigma 1 norm of gradient U times a small factor eta. And the second one is the mixed norm of U minus W, L2, L sigma. It can be bounded by L sigma 1 norm of F plus L sigma 1 plus kappa 0 norm of gradient U times a small factor eta. Here the point is the sigma 1 plus kappa 0 is this number is large, but we will have a small factor times this, and we remark here the mixed norm in the left hand side in here can be replaced by the L sigma norm with respect to T and X. The step 2 is to estimate the regularity of solution to homogeneous system. That is this system. We will prove that for any beta 1 greater than this power, this number will be larger than P in our case. And we will prove the L beta 1 norm of gradient W can be bounded by LP norm of gradient W and the mixed norm of A. The mixed norm of A. And moreover, we will prove the L infinite norm of gradient W can be bounded by the L beta 1 norm of gradient W to some power by iteration. And we remark here, this result is also a homogeneous result. From step 1 and step 2, we see that if we want to get the L infinite norm of gradient W, we need to estimate this. And furthermore, we need to estimate A and LP norm of gradient W. So in step 3, we will estimate A and LP norm of gradient W. First, we estimate A. A is the mixed norm of W minus W2R, where W2R is the average of W in B2R. So A can be bounded by the mixed norm of U minus W and U minus U2R. Here is term 1 and term 2. For term 1, we will use comparison estimates. It can be easily dealt with. And for the second term, it is the mixed norm of U minus U2R. we use the Poincare-Sobolev inequality to get term 2 bounded by L sigma 2 L n q0 over n plus q0 norm of gradient u. Note that these two numbers are both less than sigma 1. So we can get the term 2 can be bounded by L sigma 1 norm of gradient u. And next, we estimate LP norm of gradient W. We use comparison estimates to get LP norm of gradient W can be bounded by LP norm of gradient U minus W plus the LP norm of gradient U. And this term can be bounded by the comparison estimate. And combining step 1, step 2, estimate of A and LP norm of gradient W, we can get the L infinity norm of gradient W can bounded by these three parts. And here we mentioned that here eta is a small factor, comes from the comparison estimate. And second, we will prove the L sigma 1 norm of gradient U minus gradient W. This will be done by using the interpolation between LP norm and L sigma 1 plus kappa 0 norm. And for the red part, we can bound it by eta square times the L infinity norm of gradient W. Then combining this inequality and the comparison estimate and the estimate of L infinity norm of gradient W, we can get the estimate of L sigma 1 norm of gradient U minus gradient W. And we can let gradient W equal H. Then we can finish the proof of theorem 2. So next, we go to the comparison estimate. Recall that we have proved, we have stated two comparison estimates. The first one is LP norm of gradient U minus gradient W can be bounded by LP of F and plus L sigma 1 of gradient U times a small factor eta. And the second comparison estimate is the mixed norm L2 L sigma of U minus W can be bounded by this plus a small factor times this. First, we show how to prove the LP norm of gradient U minus gradient W. We set F equal U minus W. Then the equation of F reads as 13. And using F as a test function in 13, and we can easily get the estimate of LP norm of gradient U minus gradient W. Here, the eta, the small factor eta, comes from the small BMO norm of the coefficient A. And next, we focus on the estimate of the mixed norm for U minus W. We first estimate the L sigma norm of U minus W. We will use this one as test function in the equation of F and doing integration by parts, and we will get the inequality 14. For the second part, the second term in the left-hand side, we add one term. We add one term of F and minus the same term of F, and proved that this term has a lower bound F to the sigma times the gradient F to the P minus gradient u to the p minus 1 times the gradient f times f to the theta. And then integrate in time in 14, we will obtain here is E3 plus E4 is less than E1 plus E2. We mentioned that if U is a scalar, then F is a scalar, and then E2 equals 0 here. And next we will estimate E1 and E2. The estimate of E1 is simple. By interpolation and Sobolev embedding, we find a unique sigma such that the L sigma norm of F can be bounded by the left-hand side, that is E3 and E4. And then we can estimate E1 by using Holder inequality, and finally get E1 bounded by this. And here we point out that the small factor eta comes from the small BMO norm of the coefficient A. And next we estimate E2, and E2 here we expect that E2 can be bounded by some norm of capital F and plus a small factor times some norm of some higher norm of gradient U. So how to do this? We can the main idea is to take some gradient F out. Here is the red part, and epsilon 0 is a small number. We take some gradient F out, and then applying Holder inequality with exponent p over epsilon 0 to this part, and then we get the red part to be LP norm of gradient F. And since we have proved that the LP norm of gradient F has a small factor here, so if we do this, we can get a small factor in the estimate of E2. This is the idea to deal with E2. Combining the estimates of E1 and E2, we can get E3 plus E4 can be bounded by some norm of capital F plus eta plus a small factor eta times a higher norm of gradient U, and then the L sigma norm of F can be bounded by these two terms. We want to estimate the mixed norm L2 L sigma. Note that in our case, sigma is greater than 2, then we can easily use Holder's inequality to get the estimate of L sigma, L2 L sigma of F, estimate of F. It is the same as the L sigma norm of F. And this is the comparison estimate. Next, we go to the regularity for homogeneous system. Recall that we stated that for any beta 1 greater than this number, the L beta 1 norm of gradient W can be bounded by the LP norm of gradient W plus some power of A. And A here is the mixed norm of W minus W2R. Once we get the L beta 1 norm of gradient W, we can prove the L infinity norm of gradient W bounded by the L beta 1 norm of gradient W by iteration. So we will prove this next. To prove this, since the system is singular, we will regularize the solution by considering the approximate system. It is a system of 15 here. We replace the gradient V to the power p minus 2 by gradient V square plus epsilon square to the power p minus 2 over 2, and set the boundary condition V equal W on the parabolic boundary of the cylinder. Then by the classical regularity theory, we can get V is smooth for any positive epsilon, and V converges to W in C1 local as epsilon goes to 0. And also we define the standard cutoff function, psi, and the psi equal 1 in the smaller cylinder and equal 0 in a neighborhood of a parabolic boundary of the larger cylinder. And also psi satisfies that the time derivative of psi can be bounded by this, and the space derivative of psi can be bounded by 1 over R1 minus R2. This is a standard cutoff function. And next, we will show the L mu plus 2 norm of gradient W can be bounded by the L mu plus P norm of gradient W. Here mu is positive. We first show this, and then we will get the result by doing this step finite times. So how to do this? We differentiating the system, the approximate system with respect to XL, and get this equation. And we apply partial XL, partial LV times this as a test function, and obtain the inequality 16. Here, the right-hand side, the blue part comes from the partial T acting on psi to the power K plus 1, and the red part comes from the second derivative acting on this part. We see that the red part is L mu plus P norm, and the blue part is L mu plus 2 norm. So next we want to prove the blue part can be bounded by the left-hand side of 16 and also the mixed norm. It remains to prove the blue part. When to prove this, we first consider the integral with respect to x, and take some integral with respect to x out, and take the L infinity norm of t, and then the remainder term is a red part, is a red term. We do this. Why we do this? We expect that the time integrability of the mixed norm can be lower. So we do this to get more room for the mixed norm. And next we will estimate red part. We first add the integral with respect to x, and here the idea is there is a gradient v square here, and we write one gradient of v as gradient of v minus vr1, where vr1 is the average of v in br1, and it is a function of t. It is independent of x, so we can write gradient v as gradient v minus vr1, and then we do integration by parts. We can get the inequality 18, and we need to estimate term 1 and term 2. We hope that term 1 and term 2 can be bounded by the left-hand side of this part of this inequality, and it is easy to estimate it by Holder inequality, and we skip the details here. After the estimate of term 1 and term 2, we integrate in time, and we integrate in time here in this inequality, and doing Holder inequality, we can get the estimate of the blue part. So finally, we let epsilon goes to 0, then v converges to w in C1, and we can get the inequality 21. That is the L mu plus 2 norm of gradient w can be bounded by the L mu plus p norm of gradient w, and plus some power of a. So this shows that we can improve the integrability of gradient w from mu plus p to mu plus 2. And for any beta 1 greater than n times 2 minus p over 2, we can apply this estimate finite steps to get the L beta 1 norm bounded by LP norm and A and the mixed norm A. So we can get the result. And I think I can stop here. Thanks for your attention.